Hey everyone, in this lesson I'm going to explain how different numeral systems work. Understanding this will help you see how values are actually stored in a computer's memory, and you'll also learn about some C++ tools that let you work with different numeral systems. So what exactly is a numeral system? It's just a way of writing and representing numbers using a specific set of symbols, like digits, and certain rules for how to use them. For example, in everyday life we use the decimal system, the one with digits 0 through 9. Using these digits, we can write and read any number, but throughout history, people have used many different numeral systems for different purposes. You've probably heard of the Roman numeral system, where letters are used instead of digits like I, V, X, L, and so on. Besides just using symbols, that system also has its own rules for forming numbers. For instance, to write 9, you put I before X, and to write 11, you put I after it. There are tons of numeral systems out there, but in this lesson I'll only focus on the ones that are actually useful in programming and can be used in C++. Let's start with the one you already know best. The decimal numeral system is the one that uses the 10 digits you already know: 0, 1, 2, 3, 4, 5, 6, 7, and 9. And 8, of course. It's what's called a positional system. That means numbers are organized by place value. First come the ones, then the tens, then the hundreds, then the thousands, and so on. For example, 9 is in the ones place. The next number already has 2 digits, that's the tens place. 99 is the biggest number you can make within the tens range. The next one, 100, has 3 digits, that's the first number in the hundreds range. That's why we call it a positional system, and actually all the systems we'll talk about today work the same way, they're all positional. Also, just to keep things simple, I'll only use positive numbers in my examples. We'll deal with negative ones in another lesson later on. So the smallest number in the decimal system is 0, then comes 1, and so on. Once we reach 9, we realize that's the biggest number we can represent using a single digit. So what's next? After that, the ones place resets to 0 and the tens place increases by 1. That gives us 10. Then we start increasing the ones place again until we hit 9. The next number after that is 20. The ones place resets again, and the tens place increases. I'm sure you already get how the decimal system works. We've been using it our whole lives. Up to this point, we only use decimal numbers in our programs, but in programming we can also work with other numeral systems. There is also the binary numeral system. It only has 2 symbols for writing numbers, 0 and 1. Sounds too simple, right? Can just 2 symbols really represent any number? Absolutely. Let's see how. We start with 0, the smallest number in the binary system. Then comes 1. What comes next? Since this is still a positional system, it also has place values, ones, tens, hundreds, and so on, just like the decimal system, but based on 2 instead of 10. The ones place in binary includes 0 and 1, but the next number after 1 is written as 10. So what happened here? Once we reach 1 in the ones place and need to increase the number by 1 more, we reset the ones place to 0 and increase the next place, the tens place, by 1. That gives us 10, which is actually 2 in decimal. What's next? We increase the ones place again, and now we have 11 or 11. That's 3 in decimal. And now we hit another limit. The next number has to be 100. To get it, we try to add 1 more to 11. Since the ones place is already 1, it resets to 0 and adds 1 to the next place. But that place is also 1, so it resets too, and we add 1 more place on the left. That gives us 100, which equals 4 in decimal. And that's how it goes. Using just 0 and 1, you can represent any number. The only difference is that binary numbers tend to be much longer than the same numbers written in decimal. Why do you even need to know about the binary system? because that's exactly how data is stored inside a computer. Everything in a computer's memory exists in binary form. Memory is made up of bytes. A byte is the smallest unit of memory that has its own unique address. Let's take, for example, 8 GB of RAM. What does that actually mean? 1 GB equals 1024 megabytes. 1 megabyte equals 1024 kilobytes. 1 kilobyte equals 1024 bytes. So when you buy 8 GB of RAM, that means your computer will have 8 billions 589 millions 934,592 bytes, individual memory units that each hold some kind of data and have their own unique number, which we call an address. But each byte is made up of 8 bits. A bit is the smallest piece of information possible. It can be either 1 or 0. So if you line up 8 bits in a row, choosing either 0 or 1 for each, you get a combination that represents one full byte. Now, let's say I create a variable that stores the number 10. The variable has the type short. Remember how much memory a short takes? 2 bytes, that's 16 bits. So if we write out 16 zeros, that represents the full memory space taken up by one short variable. We want to store the number 10 in it. In our code, we write it in decimal because that's what's natural for us. But in memory, the number isn't stored as 10, it's stored as its binary representation, and it's stored from right to left. In binary, the number 10 is 1010. That's what's actually saved in memory. The same thing happens with any other data type: long, float, double, char, bool, and so on. It doesn't matter whether you're working with integers, floating point numbers, characters, or even the literal values, true or false. Every single piece of data in memory is ultimately stored in binary form. In C++, you can write number literals not just in the decimal system, but also in binary. To do that, you simply start with 0b, followed by a sequence of ones and zeros. If you try to use any other digits, you'll get a compile time error. When you hover your mouse over such a literal in your IDE, the tooltip will usually show you what that number looks like in the decimal system, which helps you understand it more easily. You can also use a single quote to visually separate groups of digits. It doesn't affect the number's value in any way, it's just for readability. By default, numbers are printed to the screen in the decimal system, but you can also output them in other numeral systems. I'll explain how to do that a bit later. Now, let's move on to the octal numeral system, the base 8 system. It uses the digits 0, 1, 2, 3, 4, 5, 6, and 7, so there are only 8 symbols in total. It works the same way as the other positional systems we've talked about. The smallest digit is 0 and the largest is 7. You've got the ones place, the tens place, the hundreds place, and so on. From 0 to 7, everything looks just like in decimal, but after 7, the next number is 10, because the ones place resets to 0 and we increase the next place value by 1. Then we go 11, 12, 13, all the way to 17. After 17 comes to 0, which equals 16 in decimal, or 10000 in binary. So why do we even need the octal system? Honestly, these days we don't, but it's still useful to understand why it existed. The key reason has to do with the word size of early computers. Back in the 1950s, 1970s, computers didn't use 8-bit bytes like we do now. They often worked with word sizes like 12, 18, 24, and 36 bits, all of which are divisible by 3. One octal digit represents exactly 3 bits. Numbers from 0 to 7 can be written in binary as 000 to 111. That made octal compact, readable, and convenient for engineers. Binary numbers were too long and hard to read. For example, look at this. Hard to tell what it means, right? And decimal didn't line up cleanly with bits either. It didn't show how the data actually looked in memory. Octal was a nice compromise. Every 3 bits became 1 digit, which made working with machine code a lot easier. The octal system was widely used in early computers like PDP-8, PDP-10, CDC, and UNIVAC. Addresses, registers, and instructions on those machines were often written in octal. It was also popular in assembly language because octal notation directly reflected the bit structure of the commands. You can still see traces of octal today in Unix systems. The most famous example is file permissions. When you type a command like chmod 755 file, each digit represents 3 bits of permission settings. But octal eventually disappeared from modern programming. The main reason is the standardization of the 8-bit byte. Starting in the late 1970s, a byte became defined as 8 bits, and the char type was standardized to 8 bits as well. Data sizes started being built in multiples of 8. Since 8 isn't divisible by 3, octal became inconvenient. It was replaced by the hexadecimal system, which fits perfectly with 8-bit bytes, but we'll talk about that later. That said, C++ still lets you write octal literals. To do that, just put a single 0 before the number. Everything that comes after that 0 is treated as an octal digit, meaning you can't use digits higher than 7. And if you hover your cursor over such a literal, your IDE will usually show its decimal equivalent. C++ also has a stream manipulator that lets you print numbers in octal format. It's called stdoct. Don't worry if you don't know what manipulators are yet, we'll talk about them in a separate lesson. For now, think of them as output settings. You can write stdcout, stdoct, and after that, any number you print, whether it's binary, decimal, or octal, will be displayed in octal form. If you want to switch back to decimal output, use the stddec manipulator, short for decimal. Unfortunately, there is no built-in manipulator for binary output in C++. Alright, so finally let's talk about the hexadecimal numeral system, or base 16. This one uses 16 symbols to represent numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the letters A, B, C, D, F. That's 16 in total. It was created to make working with bits easier in modern computer systems. The hexadecimal system turned out to be much more convenient because each hex digit corresponds to exactly 4 bits. That means a single digit from 0 to F represents the binary range from 0000 to 11111. Since 1 byte equals 8 bits, you only need 2 hex digits to represent 1 byte. Just like other positional systems, hex also has ones, tens, hundreds, and so on. In decimal, each position goes from 0 to 9. In octal, from 0 to 7. In binary, from 0 to 1. And in hexadecimal, from 0 to F. So hex digits 0, 9 match the same values as in decimal, but then we move on to letters. A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. The largest single-digit number in hex is F. After that comes 10. For example, FF in hexadecimal equals 255 in decimal. Since a byte is made up of 8 bits, which can be split visually into 2 groups of 4 bits, each group can be represented by a single hex digit. So 1 byte can look like this, 2 hex symbols side by side. No matter what the actual bits are, you can replace them with their hex equivalents. You should also know that 1 byte can store numbers from 0 to 255, meaning there are 256 possible combinations of ones and zeros in a single byte, or from 0 to FF in hexadecimal. C++ also supports hexadecimal literals. To write one, start with 0x, then type your digits, and you can also use the letters A, B, C, D, E, and F. Any other letters or symbols will cause an error. If you hover over such a number in your IDE, you'll see its decimal value for reference. C++ also has a string manipulator for printing numbers in hex form. It's called std hex. Just write stdcout, std hex, and from that point on, any numbers you print will appear in hexadecimal format. By the way, remember when we printed memory addresses earlier? Those addresses are, by default, displayed in hexadecimal. That's why you often see letters A through F in them. If you ever want to display an address in decimal instead, just convert it to an integer type before printing. While back, I recorded a lesson about escape sequences, but I didn't cover all of them. There are 3 more you should know about: /number, /x, and /u. If you write a backslash followed by 3 digits, and each digit is no greater than 7, that sequence is interpreted as an octal number. For example, if you write something like this, you'll see a capital letter A appear. There is also /x, which is used for hexadecimal values. After /x, you can write digits from the hexadecimal system, like this, for example. In that case, the characters are interpreted as a hexadecimal number, and again, you'll see a capital A appear. And finally, there's /u. After it, you write exactly 4 hexadecimal digits. This escape sequence is usually used with types that support the UTF-16 format, for example, the char16t type. You'll often see it together with a U character or U string literal. If you use an uppercase /u instead of lowercase, it switches to UTF-32. In that case, you'll need to use the char32t type along with uppercase U literals for characters or strings. I could go on for a long time explaining how to convert numbers from one numeral system to another, and I actually have many times back when I used to teach this stuff. But after working as a programmer, I realized something important: you don't really need to know those conversion algorithms by heart. It's just not practical. You already have a calculator, and that's more than enough. Let me show you what I mean. Open the calculator app on your computer. In the top left corner, switch the mode to programmer. On the left side, you'll see labels like hex, dec, oct, and bin. To the right, there's a number display that starts with 0. These represent the same number in 4 different numeral systems: hexadecimal, hex, decimal, dec, octal, oct, and binary, bin. For example, let's say I want to type a number in hexadecimal, specifically AB. I select the hex mode, and now the calculator shows a column of letters. I press A and B, and I can instantly see what that value equals in other systems: 171 in octal, 253 in decimal, and 10101011 in binary. This way, you can easily enter numbers in any of these systems and instantly see their equivalents in the others. But hey, if you're really curious, feel free to Google how those conversion algorithms work. They're not difficult to understand. It's just that, personally, I've never actually needed them in real life. Still, if you enjoy learning this kind of thing, go for it. Okay, let's wrap it up. In 99% of cases, if not 100, you'll mostly be using the decimal system, since that's the one we all naturally understand. However, from time to time, you might come across hexadecimal or binary numbers in code. That's totally normal. I've seen it plenty of times myself. The main thing is just to recognize how these literals look, so you don't get confused when you run into them. Once you know what you're looking at, there's nothing to worry about. And that's it for this lesson. Thanks for watching. If you enjoyed this video, you can support me by liking it, leaving a comment below, subscribing to the channel, donating via the link in the description, or using the YouTube thanks button, or by becoming a channel member to get access to practical lessons where you can reinforce what you learned in this lesson through hands-on practice. All of this helps promote the channel and motivates me to keep making videos for you. Happy studying and see you next time.